Hello everyone, and we're very glad you could all join us today. I'm Eli Leland, CTO and co-founder at Voltaic, and I'd like to welcome you to our webinar where we'll be talking with our guest Puneet Sinha about the battery production problem, essentially why it's so hard to get started producing batteries at giga scale. First, a couple housekeeping notes. We welcome and encourage participation from our audience today, so please do submit your questions through the Q&A function of your Zoom app. Note that the participant chat is disabled, so don't use the chat to submit your questions. Use that Q&A function. And again, we will be running a couple polls, including one that should be active now. So please have a look at those and participate. And now to introduce our panelist. Our featured panelist today is Puneet Sinha of Siemens Digital Industries Software, where he is Senior Director and Global Head of the Battery Industry Vertical. Puneet has a PhD in Mechanical Engineering from Penn State and extensive past experience developing and commercializing batteries and fuel cells, including several years leading teams at GM. Joining us on today's panel is my co-founder and Voltaic's CEO, Tal Schulklopper. Tal has also been working on electrification technologies for over 20 years with extensive hands-on experience developing and commercializing fuel cells and grid storage batteries before joining me to start Voltaic in 2012. And so with that introduction, I'm going to turn it over to Tal to present some introductory material to frame today's discussion.
Awesome. Yeah, so good morning, good evening to everyone. And yeah, today we're just going to talk about, some of the key problems in the battery space. And there's a myriad. We're not going to cover them all today, but we're just going to have a discussion, a lot of what Voltaic and Siemens are seeing out in the market, and welcome the audience to really bring up some of the challenges they're seeing and have an open discussion here. And so, many of you have seen this up front, but, the reality here still is even for those who have launched gigafactories before, it is a continuous challenge to actually bring these new factories online. And even once they're online, anytime you're doing an upgrade or you're doing additional facilities or, process changes, it can be a very slow and challenging process. So we like to talk about two of, case studies from the last decade that really are exemplar. The first, gigafactory in North America was announced in 2014. It started production 2017. And over that next 4 years, they had a tremendously difficult time actually scaling up and decreasing scrap rates from that factory. So at the end of the first year of production, there was a public report that mentioned that they had an 84% scrap rate at the end of that year from that facility. And if you think about it, that is a tremendous amount of material and loss and just lack of revenue coming out of that massive capital investment. And then they finally got to profitability in Q1 2021, and even then it was a pretty small profit. And so that's a 4-year period where you made this tremendous capital investment, got the facility ready, you had thousands of people on staff, and you weren't making any money. You were actually losing additional money. And so that's a huge investment. And then this is a common theme. There was a large European gigafactory in Poland that was announced 2015, started production 2018. And then there was multiple years of, there was a whole range of OEMs in Europe that were depending on batteries coming out of that factory. All of those vehicles, by and large, were delayed. There was a number of recalls of batteries from that factory, even as late as early last year as well. And then additional facilities in the U.S., some of these joint ventures have had, pretty public delays and yield ramp as well. And so it's something that is continuing to this date. And so if we look at it as a whole here, there's a couple of these key challenges. One is this slow yield ramp. So, people are making these tremendous investments and then having high scrap rates, 84%. We've seen from another customer in Korea last year, they were at 99% scrap rate after a year of production. And so they had some spurts where they got above, but most production runs, just about everything was scrap. And it's something that we hear relatively often. And then the time to profitability, it's quite challenging, especially as cell prices have dropped. And so you really have to be at high yields in order to hit profitability. And so, no one's going to make these huge capital investments if it's going to take 4 or 5 years to get to profitability. And then even once you get to scale, quality issues, at the back end could really, kill your profitability. And so, even if you get to that 90% yield, which is a good initial benchmark, um, those scrap rates are really going to minimize any profitability from that factory. This scrap not only, costs you from cells you can't sell, but is also costly because you have to pay someone away to take that, toxic material away and recycle it. And then on the back end, there is this, dichotomy where, the cell supplier is really trying to get those cells out the door and sell them. But if they, open up the tolerances too broadly and put bad cells out into the field, it could lead to recalls, early returns, and that's going to really on the back end, kill profitability as well. So it's a really tough challenge here. And so the big question here is why does this process, take so long? Why does it take 4 years to get to profitability? Why is our scrap rate so hard? So if you look at the production process, there are literally, thousands of different control points for different materials inputs, processes, equipment settings, building controls, etc. And if you look at the feedback cycle, it takes a couple of hours or, a day, if you can call it, to make a battery cell. And then you finally finish assembly of that battery cell. And then the challenge here is you end up taking, 10 to 30 days, sometimes longer, when cells are in customers' hands until you realize cells have failed qualification. And so, the big challenge here is these really long feedback cycles of understanding if you had good or bad finished cells. And then even once you realize you have a problem, there are thousands of these upstream process parameters, settings, and tolerances that really have to be fine-tuned, sort of in parallel to really get cell quality up. And so again, just to look at this another way, you identify these problems 2 to 3 weeks post-production, and then to figure out the root cause, with a lot of the current data systems and infrastructure, it is literally going machine to machine and trying to look at correlations and trying to figure out where these problems came from. Some of them may be interlaced. And so it's very difficult to actually figure out where these problems come from. And so as you ramp up this factory, you have to go through dozens of these iterations to try to figure out and really dial in those tolerances. And that's what adds up to years here. And so during that ramp up phase, as you go through this process and are generating a lot of scrap, it is incredibly expensive as you're essentially burning money, feeding money into the machines and burning it as you're trying to ramp up. And so you have to try to speed this process up. And so we look at the economic impact of doing this for new factories. Right up front here, you're making this very large capital investment in, you're getting a facility set up, you're putting money into getting that up and running, you're buying capital equipment, you're hiring people, and then the OpEx costs really ramp up as those people are there, you're buying materials, you're starting to produce stuff. And if you're not making good battery cells, that leads to just tremendous continuing losses. And so those self-funding points, if you projected $1 billion, it may end up being $2-3 billion if you look at those operating costs as you're not producing cells you could sell. And then finally, you get to this, self-funding point and then the break even for the factory. And so the opportunity here is really to accelerate that process. If we could shift this left, shift the learning forward, whether it's with early identification of problems, simulation, and really trying to understand these processes, you could really, speed up this entire process and shorten that feedback loop. The next part here, both for new factories and existing factories, is really around the net profit out of these facilities. And so typically you have this pretty low ramp up to getting to profitability. And if you could shift this left, you could not only, recover this lost revenue during that slow ramp up, but you could also be more profitable long term out of these factories. If you could have that higher yield rate or lower scrap rate, that's going to mean more profit at the end of the day. Facility is, during long term operations as well. And so, one of the parallels we really like to show for the battery industry, all is not lost. It's not all doom and gloom. There's been a range of other industries who've been through a very similar journey. And we really like to, call out, the transition that the semiconductor industry went a few decades earlier. And so this is a chart here showing the market size for the semiconductor industry from the 60s to the 2010s. And the batteries are just a few decades behind that. And so the early days for batteries in the 90s and 2000s, it was really consumer electronics dominated. And so you see this low, slow and steady growth here. Then you start to see this uptick. So around the 2010s, we started to see this EV and now ESS dominated growth, really starting to ramp up the need for battery cells in production, increase the market size. And then everyone assumed that we were going to have exponential growth, 300, 400, whatever the number is, gigafactories coming online within the next 5 years. Oh no, we're not going to have enough materials. And the reality is it's a lot harder to make these factories. So you get this initial trough of disillusionment as well. Early scaling is very hard. So some of these factories are going to come online. It's going to take longer. We don't have a lot of the talent. We don't have the infrastructure in place. And then finally, with the semiconductor industry, you see this after about a 5-year period, you start getting into that actual exponential growth. And then finally, market maturity. So right now in the battery space, we're in this trough of disillusionment, this early scaling challenges. And the semiconductor industry made it through this transition. And a couple of things that we saw there, we saw a lot of standardization come into play. We saw a lot of training programs. We saw better metrology. We saw a giant equipment industry, software industry really develop around this as well. And so the battery industry is here at this early phase. And if we look at the semiconductor industry as an example here, really only those companies that are going to figure out how to ramp quickly and achieve higher yields are going to achieve survival. And so in the semiconductor industry, we saw the market that was hundreds of different players really narrowed down to into the tens of high performing, highly profitable players at the end of the day. That is likely to happen in batteries as well, but really the companies that put in that infrastructure to be able to scale effectively are going to be able to make it out of this transitionary period. And so coming up here, we're going to move into the next stage here, this maturing battery production. We'll start talking about just a couple framing questions and some of the big challenges, but then also really dive into a discussion. So we're going to have a couple seed questions that Puneet, Eli, and I will start diving into, but really question additional Q&A for the audience. So please chime in and we'll work in your questions here as well. And I think also right now we have an additional poll coming in on what you see as the opportunities here, the biggest opportunities to improve battery production. So that should come online here shortly. And then one thing to emphasize, one thing I know Puneet and I often talk about with customers is, a lot of people want to think about these problems down the road once the factory's up and running. They want to start dealing with these questions later. Like priority one is just getting the facility or getting the equipment. And really what we emphasize is, you really want to do this as early as possible. You want to shift these decisions and these learning up in the process. So those learnings that you could do in that, R&D stage, figure out really what is that material, that process, how this thing is going to scale. Start to look at simulating what this is going to look like in a larger scale production facility. Then you go into this pilot facility and then gigafactory. So take those learnings and try to utilize them as you go to the additional stages. The reality here, if you look at the amount of people, the costs, the budgets, if you're trying to do this learning at the gigascale, you're looking at, hundreds of thousands or millions of dollars per production run. That is an incredibly expensive way to learn when you could do much lower cost learning at these earlier stages. So the sooner you can start understanding your processes, your materials, your tolerances, how these things are going to perform at scale, really it pays dividends here. So start figuring out what's, recs you need for your equipment, how this thing is going to scale at a larger scale, pilot facility. But yeah, really shift that all left. And so, yeah, for the discussion here, we've centered the battery production problem around like these three core areas. People. So people are one of the big challenges. There hasn't been a lot of experience making batteries at scale across the industry. It's been a handful of small companies. And now we're trying to do that across the globe, many facilities all at once. Processes. So there's a whole range of processes from procurement to how you actually run and do these things at scale that are a big challenge here. And then procurement and the actual equipment that you need for these facilities. So with that, I think we'll tee up the first set of questions and start the discussion.
Excellent. Thanks, Saul, for that introduction. Yeah, we chose to go with an alliterative selection of sort of themes and topics to frame this discussion: the people, process, and procurement. Procurement being equipments and systems. So to start off the conversation around people, we have a couple framing questions here. One involves, the use of consultants to get ramped up. Another route that we see companies taking is to hire expertise from existing leaders, say Tesla or any of the other major global cell producers, and then some questions around the suitability of internal resources, whether it's IT teams or internal AI teams, to help provide some of that digital infrastructure and infrastructure around learning. So to the panelists, I guess, let's start with consultants. What do we see as the role of consultants in helping to bridge the gap in terms of the lack of people? And what other approaches do each of you see companies taking? Let's start with you, Puneet.
First of all, thank you, Tal and Eli, for having me on this webinar. It's a great topic, very timely. Before I go and answer the question you put in, it is very critical to reemphasize some of the things that Tal said, that when we look at the problems of battery production, and even through the dimensions of people, process, or procurement, the problem is that at the core of it is that the traditional engineering and manufacturing practices that were developed and mastered for previous technologies don't fundamentally apply to batteries. And the reason, if you look at it from a first principle basis, batteries require very strong interaction across multiple domains: materials, chemistry, mechanical, electrical, electronics, thermal, software. All of these domains interact very strongly while you're engineering a battery, or even when you have to go and manufacture it. And these interactions were either weak or not present in the previous technologies. Like if you look at IC engineering, you don't necessarily need to, you can do a lot of the work in silos and try to bring all of them together at the end. In the world of battery, you make a small change, even let's say for a binder material, which is not even something that acts in adding energy or power to your battery. A small change in material has a strong implication on manufacturability, very strong implication on life or the durability of the battery. So again, it is very hard for companies to rely on, hey, I'm going to build a prototype, I'm going to test it, and then I'll tweak it, or I will test and tweak. Those kind of methods that were built and mastered and passed, they don't work. So when I go around and talk with various companies, and one thing is common, they all are at different stages of their businesses, but one thing is very common is they all agree with this basic fact that, hey, what worked for us, I mean, even the industry leaders, what worked for us 10, 15 years back when we started our production and scaled up our production is not good enough anymore, because, hey, technology is changing very fast. I still have to worry about a lot of OPEX, CAPEX, and for the new players, I mean, if they have to catch up, they don't have the luxury of the time and experience that, Samsung and LG and Caterpillar could spend in last 10, 15 years. So because of that, companies are looking at, hey, what can I do to learn fast? And in order to do that, they are looking to say what the data that is coming out, the digital world, how it can help me. And this is where they are saying, consulting company, like if you look at Capgemini and Deloitte, a lot of the work that they are doing, and from Siemens side, we partner with them as our in our ecosystem. And I talk to them, that is one of the number one things that a lot of companies are looking at. Consultancy help us define that roadmap for a digital roadmap. What are various systems I need to look at? How they need to all be coming all together. So have that framework and definition. And that is getting very critical. But again, at the bottom of it, whether somebody applies it by themselves or leverage consultancy, it is absolutely critical in the market right now to have a digital framework for companies to play with what technologies they want to engineer and how they want to manufacture it, right? Even it's not just at the engineering and simulation, but even the factory they want to set up, how the materials will be flowing, where the different machines will be sitting in the factory. All of that they need to and they want to do it in the digital world, but then they need to have a way to manifest all of those things in the real world. So that digital to real connection is very critical. A lot of companies are looking to do it leveraging consultancy to drive that roadmap. A lot of them are looking to take it in-house by themselves.
Thank you for that, Puneet. Yeah, that was great. Tal, turn it over to you. So, it almost seems like an insurmountable problem if the human experience doesn't exist in the volume that is needed to support, let's say 10x that this industry is going to scale over the next year or more. How do you see companies addressing that and filling the gap, through any combination of whether it's consultants, whether it's, hiring experts from other companies that have done it before, or assembling teams with the required skill sets, even if they don't necessarily have it coming from the battery industry? I wonder if you could comment kind of on those things. And in particular, if we're looking to broaden the base of talent that we're looking for, what kinds of skill sets are relevant?
Yeah, I think just going back actually to one of the first things Puneet said, just the fact that batteries are so interdisciplinary, you hit so many domains and realms, those, old powertrain engineers, the manufacturing engineers, I think at the core of it, you need to build this organizational structure and digital architecture within your organizations to facilitate communication across teams and just rapid learning. So many things that are, assumed right now to be copy paste, just give me, X from, the same thing that Tesla had or CATL had. It just doesn't work because, there's a lot of these local changes. You're making a slightly different cell, you're making a different form factor, you're making, and yeah, it's really around the digital infrastructure and culture that is going to communicate. I remember especially like emblematic at a lot of the car companies we deal with, there's 8 different teams dealing with the same battery data, but they don't even barely ever talk to each other. They don't really communicate. They all do their own different thing. And it just doesn't, that kind of learning process across those teams is too diffuse. In batteries, there's a question here from the audience around, the passover between the cell designer and the production team. And there's just so many of these, like a battery factory, like talk about is 3 different factories all in once. You have or maybe even more. You have the incoming inspection, you have the electrode, you have the assembly, and you have the end of line processes. Those teams need to be communicating that information rapidly and in common. And the only way really to do that is implementing digital infrastructure, whether it's, Jira boards or actually systems to help and share the data systems that, Siemens and Voltaic are helping customers with. So I think that's one of the keys. And yeah, thinking through that experience, bring people who've done it. I think bring people who really look for people when you're screening, that are willing to learn and collaborate, that are just not going to be stuck. They want to learn new things. They want to figure it out. They have this tendency to go in and like keep digging and try to figure out what the problem is and improve things around them. A lot of what we see, frankly, as big challenges for companies is sometimes the over reliance on consultants as well. A lot of them, they haven't seen this before. They could play a big game. They hired one guy from Tesla, they hired one guy from LG or a couple, that one person had a very small scope within that broader factory. They haven't seen this whole scope. And so just, I think, take some of those things at face value. I think some of the consultants also should be a little more transparent as well. Um, and then, yeah, the combination of that and just trying to do a little bit too much themselves. There's like also an over reliance on, we're just going to do all this and figure it all out. And you don't have time to figure it out. You need to get to profitability quickly. And so leveraging best practice tools is how we get there. And that was one of the biggest learnings in the semiconductor industry is best practice hardware, best practice software. It all consolidated around those and not the in-house tools, because outside of one or two companies, because you can't afford to develop something and let it mature, but also just you don't have the best practices, the maturity, the stability, if you don't go down that pathway. So I know I dived into a whole range of topics there.
Well, that's great. I mean, it reflects the interdisciplinary nature of the problem. Puneet, please go ahead.
So the question that Tal referred to, that was from the audience, hey, how the cell design and interfaces with the manufacturing. So Tal gave a great response. So if I can add a little bit of color to that, right? So and this is a real example. I'm not going to tell you the name of the company. So what happens there? Like when you're designing the cell, there are engineers. Of course, they are many times electrochemists, right? Who are designing these cells. And when I say design means, hey, not only just the material, but for example, what the electrode thickness needs to be that will help them maximize the cell energy density. They're using tools, simulation tools, even if they're using simulation tools, right? And have certain digital maturity in that sense. They did it. Now they have a cell that works great when you are doing a small prototype. Can be, let's say, a small pouch cell. Everything works well. You tested those when testing said, yes, it's fine. Now you have to go and make a cylindrical cell. Right? And what has happened in these cases, they can make a pouch cell, but when they start to go and make cylindrical cells, all of a sudden, the electrode is too thick for it to be not calendared correctly. Right? So now there are two things, and these are real things that happen because now you can't wind because or too brittle. So either operators are spending a lot of time to do the DOE, okay, what can I change in my calendaring pressure or temperature to change something, right? But then also then they can come back and say you have to reduce the thickness. But if you reduce the thickness of electrode, how much? And if you change that, how the cell design changes? What about the fast charging? What are the implications of this on the durability? What about the safety and thermal runaway? All of those things are all of a sudden open. So by having this digital, what we call digital transformation, but having this connected end-to-end process, so that as you design the cell digitally, you can do the product test it, but also from the very beginning, take a look at the impact of thickness on manufacturability. And even for any case, if let's say the operator comes back and say, no, you cannot do that, then what are the changes? You don't have that much of liberty left now to go and do the whole new cycle of design cycles and validate the cell. So how you can maximize the DOE, minimize the DOE for cell design, for behavior changes. And these are real things happen. And then even one change, you are looking at easy 6 months, if not more. So this adds up very quickly. So the question about how design transfer and manufacturing, they are how the data transfer needs to happen. That's where it's a simulation, it's a manufacturing operation, but also connecting them is the PLM framework so that their design data can feed forward from the manufacturer. What is happening can come back. So all of those things are very critical to have it more smoothly running.
Yeah, and I know this dips a little bit into the process side of it, but there's also a question here is like how we've seen companies do this more smoothly. And I've seen a handful of our customers actually implement pilot facilities right next to their production facilities so they could actually start testing out some of these process changes and materials changes at a smaller scale before introducing it to their broader production line. And so creating those pathways so you're not just throwing it over a fence and hoping it all works really are key in this process. And I don't know if Eli sees another one, but one that just catches my eye is,
Go for it.
just how did the Chinese overcome all these problems, and how did the cell manufacturers in China? Because they're obviously producing at very, very large volumes, and I think it's just interesting. I'm just going back to some of the first trips to China and it's visiting cell factories, and even more recent, they're still throwing a lot of bodies, except for the very largest cell producers who have a tremendous amount of automation now. There's only a handful that have it on that side. On the other side, there is a lot of bodies still in this problem. There is still a lot of scrap, and uh, what is considered scrap is what is considered okay to ship into the Chinese domestic market is very different than what is okay for outside of China. And I just remember, I'm not going to name the company, obviously, but a large, consumer electronics company in China, and just talking to them about return rates, and they had over 16% of their cell phones that were returned in the Chinese market because of battery problems. That is not acceptable in the US market outside of something going very wrong, but it was commonplace there. There still are a lot of returns, and even on the EV side, and fires and safety issues there that are not widely produced. But yeah, it's a lot of this is still brute force. We can't afford to do that in the US where there's less local subsidies. And yeah, we would just say that is not the solution for the US. So we need to work smarter with the staff that we have available here.
So those are great observations, and I think we're sort of ranging that way naturally. So I think we can transition to the process topic, but I'll just offer a synthesis of some of the things we've heard and discussed so far. When seeking to assemble teams for a new battery production venture, it's clearly a lot of this stuff just comes down to like the basics of the kinds of people that you'd want to hire for almost any venture, but clearly people that are naturally inclined towards collaboration and communication is very important given the interdisciplinary nature of these problems. And then another thing that we've seen at some customers, ideally we'd love to see this at all, is people that are just really passionate about data and data-driven learning and insight. So, I know that might come off as somewhat self-serving given that ultimately we're a battery data analytics software company, but data is really, and a passion for data and data-driven learning is one of the things that enables someone to make the transition into the battery sector. So for example, quality engineers at battery companies are often coming from other disciplines, but what they have is a passion for data and a passion for automation and improvement using that data. And we've also seen that at some customers, where they have specialists that are just there to like look at the data, find problems and solve them. And we think that's great, and we're excited to help empower those kinds of people. So yeah, let's move on to process. We've already talked about it to some extent, but this is really more about all of the steps that it takes across those three mini factories within a big battery factory, and the umpteen steps that make them up, and the challenges around basically figuring out what that process is and how to get it running smoothly. So some of the themes we hear are things like, why don't I just copy paste, my successful factory that's already operating overseas? Another thing that we see is kind of a hyper focus on individual steps and getting some individual steps working without thinking upfront about holistically how are we capturing this information and capturing these learnings over time. And again, leaning over-indexing on leaning on internal resources that lack some combination of the bandwidth or background knowledge and skill set to help solve these problems. So yeah, as we talk about process, I guess something that has come up because we see a lot of as this industry continues to evolve. Obviously, there are established leaders and successful companies that are manufacturing batteries at giga scale with established chemistries. There's also tremendous amount of news and excitement around new chemistries, some of which are more mature, like LFP certainly seems to be taking over a lot of transportation and stationary applications. But I guess in terms of process, I'm interested to hear perspectives on, let's say framing it as standing up a new gigafactory, how much does it matter whether you're building towards an existing chemistry, say NCM or NCA, versus LFP or some more advanced new chemistry, or let's say a radically new fabrication process that uses existing materials but introduces some new. What are the sort of process challenges relatively between established chemistries and processes and the new ones?
It's interesting. We see this at both sides because we have customers who are coming from the new chemistry development. They're trying to scale up production, and then the other side is the larger factories. So let me start with the larger factory side, and I think these things are not static. If you look at these production lines of factories, they're constantly going through updates every couple of years in order to speed things up, improve tolerances, all that fun stuff. And the assumption that some of these things are not going to, they're just going to be simple and you just make a simple change and it's not going to cause any other problems. Just that assumption is, proven over and over again to cause just like minor changes, slightly different supplier, different humidities, like just so many of these little things at large scale production just have tremendous unexpected follow-on effects, and it leads to just additional things you monitor for and look for and build instrumentation on top of your facilities. On the scale-up side, I think for new chemistries, new systems, it's a lot of these things, the chemistry itself may be working well, but the production process for that new material is often not proven and is closer to an R&D scale as far as like manufacturability. And we see that often overlooked as companies are trying to hit their, expectations they set with their investors or their customers on how rapidly they can scale up. And so I think really just having those honest discussions on, what you understand about your system and how it scales, and then trying to run those experiments and simulations to understand how these things are going to scale, what are the breakpoints, what is just having those honest discussions and trying to really think about how those processes scale into production is really key, and it lets you be honest about where you are along the scaling journey with these new factories and new chemistries in particular.
Excellent. And just building on that and picking up on a theme from one of our framing questions, and I think Puneet, you might have alluded to this earlier, but something that we saw a couple decades ago in the semiconductor industry was that industry got to a level of kind of maturity and standardization where they could successfully copy paste large multi-billion-dollar semiconductor fabs from Asia to other parts of the world or what have you, and generally worked out pretty well. So that's a very tempting approach in the battery industry, one that we often hear about. But I wonder if you could, Puneet, provide any kind of observations around whether the industry is really ready for copy paste, what are the challenges around copy pasting, facility process, et cetera, and how should companies think about alternative approaches to copy paste?
Yeah, absolutely. This is definitely a valid way of companies to look at when they're scaling or if they are having certain partnership with. But if you look at it, the battery manufacturing, even to date, right, whether you are a new company or you are company who's doing large-scale battery manufacturing for a decade plus. At the core of it, a lot of it is very experience-based manufacturing. So if I give an analogy, it's pretty much that if you and I can have the same recipe of cake, doesn't mean that, and if we have the same oven and same everything, same mixer, it is unlikely that I will perhaps make the same quality of cake as some of the folks here, right? And it's just the experience that somebody else have got with the same machine, same process, same everything, right? And you can say battery industry is pretty much at that level right now, just because somebody has made a cell of this format that you want to create with the same chemistry and you're gonna get the same machines. It does not guarantee that you will get that quality and that operational efficiency.
It's interesting.
Um,
That tension, just you hear it over and over again at these factories. Like all of a sudden, it's the guy from Japan or Korea comes to the facility. He looks at the slurry. He's like, "Oh, this isn't right. It needs to mix for an extra 30 minutes."
Yep.
That doesn't scale. That doesn't work. They can't fly over all the time. They can't. You need to start building that data driven like infrastructure to like, hey, what is the viscosity when you pull this off? Like, what is that? But that is really where the battery industry is today. And I think that tension, going back to people, of the tension between the old school folks who've done this for a while, like they grew up before a lot of these data systems were around, and they just look at things and sort of know. They like to use their Excel, they like to use their Jump, and they sort of take pleasure in grabbing their coffee in the morning and then sitting there for 3 hours digging over data. Other people don't even know what to look for when they're coming into this. And so it just really that translation process
Exactly.
of modernizing this is, we're not there yet.
Yeah. And again, if you, as Tal said, if you look at that, what is needed is, of course, data is needed because that's where the knowledge is. But there are a couple of elements that companies ecosystem in general globally is understanding, but they're looking to invest a lot. Right? You need to have the right foundation from where to get the data. Right? Then if you have the data, how will you collect it at the right place, contextualize it, because there's all sort of data. For example, it's like you have petabyte of data just in a maybe let's call it a month of worth of operation, maybe even less, right? If at scale, it's a ton of data. So collecting data, are you collecting the right data? Are you contextualizing the data? But then that's where the conversation starts is, if you have data, so what? I mean, how you extract the intelligence from the data and then take that intelligent insight from the data and manifest that in the operation. So unless these things are put in that way, just because somebody has data doesn't solve anything. So going back to your point is, what people are not even know what to look for. And even people who are looking for is, I mean, once you start taking away experiences, the insight, which are very experience driven, don't scale. And even the same experienced people, just if you change the chemistry from, let's say, today's lithium-ion battery to, let's say, solid-state battery, just as an example, it's unlikely that experience will translate either, right? Even if you have 20 years of experience doing that. So when you look at that rapidly changing materials, designs, but also manufacturing machines and operations, dry coating versus wet coating, you have a lot of data, but now that there are foundational technologies that are more widely available, battery specific, be it the digital twin, be it the automation, be it the generative AI, how companies can leverage it to learn fast. And that is not only for the startup. Startups have to learn, so does Catel and LG and Samsungs of the world too. So everybody wants to learn to improve and be ahead of the curve.
Yeah, I'm going to pull a couple of things. So there's a question from the audience here on like the topic of data analysis and cycling battery data and how important that is for battery production. And it actually ties sort of to a process question that we often get. It's like, oh, can't I just fix this problem? I have to worry about this problem in the coder. We're getting ununiform coats. We're getting X or Y. There's the one thing we see in companies that are producing at scale versus the companies scaling up is the companies producing at scale understand what is okay within those tolerances. It is not black or white. There's often actually a gray scale in here, and they understand how to understand that gray scale of, hey, there is some deviation. There's some bowing in the, coat that you're doing. Some of that is okay, and your cells are going to be fine. And understanding that is key. And the way you start understanding that, those are things that were within top tolerance of your coding process. The big question here is that battery going to cycle long enough? Is it going to meet your warranty requirements to customers? And the only way you can start really understanding that is with that charge and discharge, we call it a heartbeat of the battery. That initial heartbeat is an initial formation when you first start charging it. But then that, continues over the lifetime of that battery as it is operating, as it is charged and discharged. And so really the formation is that first signal to start looking at the variability and defects within those batteries that, are going to be in that gray area or within those tolerances of this is a good coating, but understanding if it has larger variability or internal resistances, or if it has slightly different, charge, capabilities. There's a whole range of these kinetics and things that we look for that you can start looking at within that cycling data. And so we think it's very important to really shift left and start to understand, you can't wait 10 years to see how this is going to cycle in a vehicle. You have to start understanding that as early on in the process as possible.
Awesome. And I want to tie another audience question, just one last sort of conversation topic on process before we move on to the final segment. There's an audience question around, is the problem not just gathering the data, but having the right type of sensors for inline data collection and edge computing? So I'm gonna sort of interpret that question as, Puneet, you touched on this. It's like, what is the right data? How do you figure it out? Because it feels like there's an almost infinite number of parameters that you might consider and track in this sort of modern data-driven, learning-driven production environment. And I'll just throw out some numbers that we've heard, from our work with different customers. When setting up a pilot line, there might be as many as 13,000 or 15,000 different individual data points that you might track across your production. And the question arises, how do we know which ones we should track? And then we've also heard from some best practice, like global gigascale leaders, that in practice, they're tracking around, 3,500, let's say 3,500 parameters on the production line to keep their process. So what is that? How do you down select? And then another thing we've heard from customers over time is like, we're just starting for the first time, how do we come up with our initial control plan? And again, I kind of interpret that as like, what are the data that we should be tracking, and what are the tolerances that we should start as our initial guess? Sort of I guess the real question is, what's our best practice advice for companies getting 0 to 1? Right, you've got your equipment, you've got everything wired up. How do you know exactly which things to look for and where to even begin in terms of all your control set points in that process?
Yeah, it's a great question, right? And I wish there was a single line answer for it, right? But I think what is needed is some of the following things, right? So maybe we need to come from there. See, when you are setting up a factory, right? It is unlikely that you are going to get all the machines from one machine vendor. So what you have all of a sudden, you have machine from few machine vendors. They have their own interfaces of how they're going to operate. So how you going you need to set up the PLM and simulation and digital twin framework, but then that needs to interact with your operation technology, like your machines and automation and whatnot. So having that IT OT integration for manufacturing, and I'm not talking about giga scale. I think it is very critical that is looked at even at a pilot scale level, where so that once you have that IT OT integration working from the pilot scale level, where you have liberty and scale to try different things, helps to build that knowledge, but also discretize or democratize that knowledge, so that, for example, you're collecting data, you can play with the machine tolerances that work for the material chemistry that work that you have in hand, but then how all the data that you are even collecting from the pilot scale that is feeding into a lot of the machine learning models for predictive maintenance. So how those controls needs to be tweaked rather than stopping and doing manual operations. So all the things that you are learning at the pilot scale or iterations at the pilot scale, if you start connecting with the data, which is based on ITOT convergence foundation, on top of it, some kind of IoT layer, where you are connecting all the machines and controls, and then a layer of battery intelligence. And that is the reason, we, Voltaic and Siemens, we are working closely together to bring this whole vertical stack. Once you have that, then even from the pilot scale, companies are able to find those things, what the tolerance makes sense for the operation they have, for the application they want to go after, right? And that makes it easier to find, hey, is it a 13,000 data points? Is it 5,000? What are the inline measurement I'm having? How am I collecting that data, or how do I need to contextualize and leverage that data? Because there is the power in this is the data, but the problem also is data. If there can be too much data and you can drown, but if you have the right harbor, you can definitely maximize the power of that is in the data.
And that gives an opening for one more a question from the audience, which is I'll sort of interpret it a little bit, but is it a greater challenge to actually learn as you scale to get the insight, or is it a bigger problem to act on the insight and implement processes that fix them in a durable way? Or how do those rate? How do those compare?
From my perspective, I think they're part of the same equation. If you are just looking at data just for the fun of looking at data and getting insights are of no value if you cannot act upon them, right? So the power that I am seeing with our partnership and how we are, and the conversation we are having together with customers, is that is like how you collect the data, extract the insight, but help me change my operations based on that insights in that continuous improvement perspective, right? So the way I look at it, if companies are putting in effort, why don't you do the whole thing rather than stopping it at the half point?
Yeah, democratize that data and create those infrastructure and culture internally to close that loop is really key. It's not a one-time problem. One of our advisors who used to work at the largest gigafactory in the world described battery manufacturing as an unstable equilibrium. There's always something trying to push you off the edges into high scrap rates and yield issues. And so it is a culture of continuous learning. And in order to really do that at scale quickly, especially as you're making, millions of batteries or tens of millions a day, you need a data infrastructure. You can't do it without those tools.
Yeah, and just to emphasize that, it almost sounds cliche, but just a culture of continuous learning and improvement is so vital in success here. So for the last few minutes of our session, I think we should transition to the procurement common theme. So these are challenges around actually getting the physical plant set up and getting it set up in place. So things that we hear in the market are, just give us what some other global leader has. Or just go for put out a bid and get the lowest cost equipment, or buy a turnkey production line. What are some of the what are some of the challenges that we see, and perhaps best practices for companies that are looking to actually set up their first whether it's a pilot scale or giga scale production facility?
If you look at machine builders, battery machine builders, battery line builders, 90% of them are in China and Korea combined. There have been studies, like McKinsey has done a study, but that is confirmed by what I have heard from customers. Right now, the lead time of getting machines can be up to 12 to 18 months. So if you are a new company, one of the challenges is how you're going to get a machine, right? So it's not that easy to say, give me what Cattle has or what LG has or Samsung or Tesla has, right? Second point, a lot of these leaders, they are not just buying those machines off the shelf. They are heavily customizing them with their own research and engineering. They have departments working on machines. Of course, they are not going to make machines, but they want to create that, what machines work for them, that accelerate the process, combine certain things, simplify it on multiple factors. And again, they also have a very tight framework of making sure the machine that they are getting is going to be something that is meeting the quality of not only for the production step, but also of the overall manufacturing process. So when you look at these factors and look at the question that you pose, Eli, I think this is what I'm heavily seeing, and where we are seeing a lot of companies working at Siemens also, is one is, rather than getting a prototype of a machine or this is what will work for me or not, it is really tough for you have to really wait. A lot of companies are saying, okay, why can't I do a virtual commissioning? And this is where a lot of that work is happening to create the interface between let's say cell supplier and machine builder. To have that virtual commissioning that create the dialogue so that you spec the right machine, right, and ensure that the machine is going to work the way you want, and installation and all will go smoothly. Second aspect of that becomes virtual commissioning is not just the mechanical, by the way, it's not just the mechanical electrical design, it's taking the whole PLC core and how the HMI will be, and the integration and debugging of all that. But also, we are working with a lot of companies to have that, what we call guidelines. So we can help based on the collective knowledge that we have built working with companies. What are some of the specs they want to put in that procurement sheet, a spec sheet when they're talking with the machine builders. So those are very critical. And again, as I said earlier, the machine builders are also looking to actively look at, hey, how can they provide that IT/OT simplicity convergence, because a customer is going to get machines from different suppliers. So again, having that open framework so that the machine can be more of a plug and play becomes very, very critical in that. So all of this is about how you can accelerate getting the right machines, right? But also in a way that you can, once you get the machine, it works where you expect it to work in your processes, right? So those are some of the key things that we are seeing. And this interaction between cell supplier and machine builder is really, really key for the success.
Yeah, just
certainly those developments in virtual commissioning have been really exciting. It's a lot cheaper to solve problems in bits than atoms. I'll go ahead and
just a final point there. I think just to keep it short, just make sure that the equipment you buy, you have open communication standards as part of the specifications. If I had to say one thing, and then a lot of this machine building industry is still relatively immature. These turnkey providers, they started off doing one thing and have cobbled together solutions. The people have been supplying some of the largest cell suppliers. These were essentially mom and pop organizations, small businesses that grew up. What the big companies have learned is they know how to, customize and just make it work with the equipment. And so just waiting for it to be perfect, it's never going to be perfect. Someone on your team has to have that culture of learning and has to just know how to get it done no matter what.
Excellent. And with that, we're at the top of the hour, so we'll flash our contact info. If you would like to follow up with any of us on any of these topics, we would welcome it. Thanks very much for the audience engagement. We had a bunch of great questions that helped direct our conversation to the things that you all are interested in. And thanks again to our panelists, our featured guest panelist, Puneet Sinha of Siemens Digital Industries Software. And we'll see you next time. We got another great webinar coming up in July. Thanks very much.
Thank you, guys.